Welcome back. This is the fifth and final part on a series of lectures on current distribution in porous electrodes. We will look at two topics very briefly: penetration depth and internal resistance. In the previous lectures, we had elaborated the significance of this non-dimensional quantity, nu square. It is the ratio of ohmic resistance and reaction kinetic resistance. It is inverse of the Wagner number. And we also clarified the meaning of this derivative, which is indicative of the reaction rate in the porous electrode. So what we observe is that when, for a particular kappa r, when nu squared increases, there is greater non-uniformity in the reaction rate. So there is greater reaction rate here, very less reaction rate here, and there's much more reaction rate here as we transition from one side of the porous electrode to the other side of the porous electrode. So what is to be noticed is that when nu square is relatively small, there is uniformity, but nu squared is large. What does large indicate here? What is the reason for it being large? That is, the ohmic resistance is much larger than the reaction kinetic resistance. That is this case. So in that case, there is significant non-homogeneity in the reaction rate. So what is the question we want to be asking? We want to connect the reaction rate on two sides. So let's say the front part of the porous electrode and the back part of the porous electrode, and then make a connection between the thickness of the porous electrode and nu squared. That is subjective here. So how do we go about doing this? So we plotted and we analyzed this data for small kappa r. So for small kappa r, this term simplifies to this term. That is, you are neglecting this term, and this entire term is approximately equal to this term. So what we can say is that, supposing at z equal to 1, that is this quantity, which is a measure of reaction rate. So at the front side of the electrode, when you plug z equal to 1 into this expression, you get this expression. And then for z equal to 0, that is the reaction rate in this section of the porous electrode. So when you put z equal to 0 into this expression, you get this expression. Supposing in our device, or that is one of the design parameter, that is the reaction rate in the front side of the porous electrode divided by the reaction rate is reaction rate at the back side of the porous electrode is about 50%. Supposing that is the design parameter. So you know this rate, that is the ratio of this to this is about 50%. And when you divide this by this, this is the expression you get. So if this is 50%, that helps me get an idea of what is nu. Once you know nu, you can use this expression to connect nu squared to the thickness of the porous electrode. So that particular thickness, in this case, we will refer to that thickness as the penetration depth. So 2 points. Penetration depth is not important when nu squared is small, but idea of penetration depth becomes important only when you have large nu squared. What do you mean by penetration depth? Okay, so one way to think about this is there are many ways to quantify, but the way we are going to qualitatively elaborate on penetration depth is the following. Okay, so the depth to which, let's say, the reaction rate is significant. Okay, so as I said, the way we are going to do is we are going to connect the reaction rate on one side to the reaction rate on to the other side. When you divide it, you get this term, and this term is using this term. You are computing this term, and this term is used for getting L. All the other terms are known for your system. So we'll move on. The last quantity we are interested in is the internal resistance. So resistance has the same definition. It is the potential drop divided by current. So that is this. For a linear kinetic approximation, we can get an expression for internal resistance. We are not going to derive this expression, but we are going to just illustrate the utility of this expression to make sense of a particular feature. So what do we see? The internal resistance is connected to L. There is a thickness of the porous electrode in this manner, and it's also connected to nu. In the previous slide, we also saw how nu squared is connected to L. Okay, so what do we observe? So when I plot our internal resistance with respect to L, what we observe is that internal resistance is large, then it becomes, there is a minima, and then it increases further as L increases. Note that this internal resistance is dependent on both the conductivity of the electronic conductor, the conductivity of the ionic conductor, as well as the resistance associated with the reaction. So all these things are combined when we derive this and when we plot this. So how do we rationalize this? So as we mentioned, all these features, that is a minima in internal resistance, is important only when you have nu squared is large. Only when nu squared is large, because that is when you have non-uniformity in reaction rate. So when L is small, what is typically seen is that there is reasonably high reaction rate for small L. However, the surface area available in that small thickness is less. So you still have fairly high internal resistance. Supposing we have large thickness, the thickness is quite large. In that case, you have lot of surface area available for reaction. However, the reaction the overall resistance is also high. So the main take-home message here is, in order to balance the constraint of surface area and the constraint of resistance, the non-uniformity in reaction rate, both these quantities have to be balanced to obtain a minima in the internal resistance. So for small thickness, you suffer the penalty of having very less surface area. For large L, you suffer the penalty of having large uniformity in reaction rate. So even though you have a fairly increased surface area. So in order to balance both these quantities, you have L at you have the minima at an in-between L, which is neither too small or neither too large. So in the next lecture, we will look at a different topic, which is related to a gas-liquid interface within a porous electrode. Thank you.